Welcome, mathletes. Here's an example involving half-life of a mythical element, mathonium. The half-life of mathonium is 18 hours. Write an equation, actually a function, m of t, that calculates the amount of mathonium left after t hours. There are a variety of ways of doing half-life problems, but the way that we tend to do them in this particular class is in function format, we would say, okay, m of t, we would have our starting amount times 1/2 raised to the t, but we adjust or scale that timing for the half-life quantity. In this problem, they don't tell us how much stuff we start with, and so you could put 100 here for your starting amount, and that could mean 100%. Right now we have 100% times 1/2 raised to the t, scaled by 18 hours. That half-life, it takes 18 hours for half of the mathonium to decompose, and then half would remain. Notice that when you plug in 18 hours, 18 divided by 18 would be 1. 1/2 to the 1 is a half. Half of 100 would be 50% left, and that's exactly what we would want. And you could check a few more entries just to make sure it's working like it's supposed to. I am going to use 100 here, not the decimal version of 100. You could use 1 whole if you wanted to. That would work just fine. And in a problem where they give you a certain amount of a substance that you start with, you would use your starting amount, like 75 grams or something to start with here. But this one we can do in this format. Compute m of 36 using the model. Tell me what it means in context of the problem. Does your result make sense? Why or why not? Well, m of 36, that means that we need to plug the 36 into the function. So 100 times 1/2 to the 36 divided by 18. And if I jump to the calculator right now and ask it for some help, 100 times 1/2 raised to the 36 divided by 18, it tells me 25 exactly. And this means that after 36 hours, (25% of the mathonium should remain. Does it make sense? Well, let's just reason our way through some table entries. This will be time and then the amount that's left over. Instantly at time 0, we have 100%. After 18 hours, we talked about this a little bit ago, after 1 half-life, 50% should remain. If you let another half-life go by, another 18 hours, that would be 36 hours, and that would mean that 25% of the mathonium should remain. And that's exactly what we got here. We just kind of launched into this and didn't do a whole lot of analysis to start with. So our results do make sense. Yes. 36 hours is 2 half-lives. So 25% of the mathonium should remain. Then I'd like to know, when will 20% remain to the nearest quarter of an hour? Well, 20% is less than 25%, so it's going to have to be more than 36 hours that go by. Let's see one way to do this with the table. Table feature was requested here. To use the table feature, we'll need to put this equation from the first portion of the problem, the model, into our graphing calculator. So y equals, get rid of any old things, y equals 100 times 1/2 raised to, we have to be really careful here, we need to use x over 18. Make sure that you have a variable in your equation. I am going to go to table set. Move this up a little bit. Table set. So I'll use second window to get to table set. I do want my table to start at 0. This second entry, this change in the table, I want that to be 0.25 because this problem asked you to work to the next quarter of, or to the nearest quarter of an hour. So 0.25 for 1/4. I do want the independent and dependent variables to be automatically generated. Once that is all set, we'll go to second table. And you'll notice at the top of your table, at time 0, 100% of the Mathonium is present. That's good. That means that we've started with 100%, and then the percentages go downward from there. That's also good. Then we start to scroll. We're looking for 20% in the Y column, 20% remaining. So we scroll, and it takes a little bit. I have skipped ahead. Now I'm down here in the 22-ish percentages. I'm getting closer. Oh, terrific. I have a quantity that's larger than 20%, and I have a quantity that's under 20%. All right. I'm going to record some of these values. Time and percentage. Let's see. It says to record several of the values from the calculator. At 41.5 hours, we had a value of 20.228. At 41.75, 20.034. At 42, a value of 19.843. At 42.25, 19.652. All right. We wanted a value of 20% of the Mathonium left over. 20% does not show up exactly in this table, so I'm going to find the value that is closest to 20%. And I believe the closest value to 20% is this 20.034. And that's the one I am going to use for my answer. So I've done the work, I've checked with the calculator, I've recorded some things, but I need to write a statement to answer the question. The question was, when does 20% of the Mathonium remain? Let's say about 20% of the Mathonium remains at 41.75 hours. This is a half-life problem. Things get cut in half every so often, every fixed 18-hour time period that goes by. But this same kind of process could work in a problem where you hear something like the number of cases of something triples every 5 days. Instead of having a 1/2 here, we would have a 3 for the tripling. Instead of 18 hours, we would have 5 days. And then if we knew the starting number of cases, that would be our A value to start with. So just because we're working on half-life here doesn't mean that it doesn't extend into other kinds of scenarios. There are lots of places in the world where this kind of exponential modeling or exponential analysis applies.